acid chloride to aldehyde. That means preparation of aldehyde from acid chloride by Rosenmund reduction. This is today's lesson. In this lesson, we are going to discuss acid chloride or acyl chloride, then Rosenmund reduction reaction in presence of palladium and barium sulfate, then examples of Rosenmund reduction, and finally limitations of Rosenmund reduction. So let's begin. First point is acid chloride or acyl chloride. Let's have a look. Carbon, double bond, oxygen, here hydroxyl group, here R. That means here R may be hydrogen, alkyl group or aryl group. When this hydroxyl group is replaced by chlorine, then this is obtained, and this replacement is carried out by adding phosphorus trichloride or phosphorus pentachloride or even thionyl chloride. Then hydroxyl group is replaced by chlorine to form this compound. This is general formula of carboxylic acids, and this is general formula of acid chloride or acyl chloride. Let's see some examples of acid chlorides or acyl chlorides. When this is hydrogen, then this is formyl chloride. If this R is alkyl group, suppose methyl group, then this is acetyl chloride. If this R is phenyl group, then this is benzoyl chloride. If this R is naphthyl group, then this acid chloride is naphthoyl chloride. These are aromatic acid chlorides or aromatic acyl chlorides, and these are aliphatic acyl chlorides. So we learnt acid chlorides or acyl chlorides. Let's move on to the next point. Now the point is Rosenmund reduction in presence of palladium and barium sulfate. The reduction in which aldehyde is prepared from acid chloride. Let's take one acid chloride. For example, this one, which is acetyl chloride. This acetyl chloride is treated with hydrogen in presence of xylene solvent at the temperature 144 degrees Celsius. That is, here solvent is boiling xylene in presence of palladium, which acts as catalyst in the reaction, and barium sulfate is used here, which acts as catalyst poison. Here barium sulfate reduces the catalytic power of palladium. When this acid chloride is treated with hydrogen in presence of boiling xylene, which is used as solvent, and in presence of catalyst palladium and catalyst poison barium sulfate, then this acetyl chloride converts to aldehyde, that is ethanol or acetaldehyde. Here byproduct is HCl. This is the reaction by which acid chloride, that means acyl chloride, is converted to aldehyde. Here acetyl chloride is converted to acetaldehyde, that is ethanol. This reaction is called Rosenmund reduction. Here, why this is reduction? In this reaction, removal of chlorine, which is removal of electronegative atom occurs, that is reduction. At the same time, addition of hydrogen, that is addition of electropositive element occurs, which is reduction. Simply removal of electronegative element and addition of hydrogen occur here. That is why it's a kind of a reduction reaction. But why Rosenmund reduction? This reaction was first reported in the year 1918 by German chemist Karl Rosenmund. That is why this reaction is named Rosenmund reduction after German chemist Karl Rosenmund, who first reported it in the year 1918. That is why this reaction is called Rosenmund reduction. Let's see some more examples of Rosenmund reduction. When benzoyl chloride is treated with hydrogen and boiling xylene at the temperature 444 degrees Celsius in presence of palladium and barium sulfate, then benzoyl chloride turns into benzaldehyde and HCl is formed as byproduct. Again, if we take naphthoyl chloride and if it is treated with hydrogen, boiling xylene at the temperature 444 degrees Celsius in presence of palladium and barium sulfate, then naphthoyl chloride changes to naphthaldehyde and HCl is formed as byproduct. So these reactions are called Rosenmund reduction reactions, named after German chemist Karl Rosenmund. In Rosenmund reduction reactions, palladium is used as catalyst that catalyzes the reaction. At the same time, here barium sulfate is used as catalyst poison, which reduces the catalytic power of palladium. If barium sulfate is not used, then this aldehyde will change to alcohol. That is, further reduction will occur if barium sulfate is not used. Similarly, benzoyl chloride, which converted to benzaldehyde, if barium sulfate catalyst poison is not used, then benzaldehyde will undergo further reduction and benzaldehyde will convert to benzyl alcohol on further reduction. So to prevent further reduction, over reduction, barium sulfate is used as catalyst poison that retards catalytic power of palladium. Now let's see reaction mechanism of Rosenmund reduction. Mechanism of Rosenmund reduction. Let's have a look. Here Palladium is used as catalyst. Its atomic number is 46. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p6, 5s2, 4d8, 4d8. This is the general electronic configuration of palladium. Here, palladium 46 in 5s and 4d orbital rearrangement occurs to get stable electronic configuration. Two 5s electrons move to 4d orbitals to form stable electronic configuration, that is 4p6, 5s0, 4d10. Fulfilled orbitals, stable electronic configuration. To get stability, this rearrangement occurs here. Now we can say that palladium has vacant orbital. This vacant orbital is the reason for working as catalyst. Let's see the matter in detail. Step 1. Suppose acetyl chloride. Here, this carbon-chlorine bond suffers heterolytic fission at 144 degrees Celsius temperature in presence of xylene solvent. Carbon-chlorine bond undergoes heterolytic fission and these ions are formed. Chloride ion. At the first step, these ions are formed. Step 2. Chloride ion combines with palladium that has vacant orbital. This chloride ion forms coordinate covalent bond with palladium. Then this is formed chlorine, palladium minus. Here palladium received one pair of electrons. That is why over palladium negative charge. Step 3. This ion combines with this ion to form this species, palladium chlorine. This species is formed at step 3. Step 3 continues in this way. Here hydrogen, palladium chlorine bond polarizes in this way because chlorine is higher electronegative atom than palladium. So here initially partial negative charge develops. For this reason electron repulsion occurs. These covalently bonded electrons move towards this hydrogen. Ultimately this hydrogen becomes negatively charged, this hydrogen becomes positively charged, that combines with this chlorine, and this hydrogen combines with this carbon, positively charged carbon. Here this carbon is positively charged and this carbon palladium bond breaks. Palladium chlorine bond breaks, from which HCl is formed. That is, HCl is formed. This palladium get freed and the compound is alkyl group. That is, here we can write methyl group. Here methyl group, oxygen, and with this carbon, this hydrogen added. So aldehyde is obtained. Here we can write methyl group. So this is the mechanism by which aldehyde is obtained from acid chloride or acyl chloride. In this reaction, palladium acts as catalyst and barium sulfate is used as catalyst poison. If barium sulfate is not used, then this aldehyde will suffer further reduction, and as a result, this aldehyde turns into alcohol. To prevent formation of alcohol and to produce aldehyde, barium sulfate is used as catalyst poison. This is the mechanism of Rosenmund reduction. Now let's see what is the limitation of Rosenmund reduction. Now, limitations of Rosenmund reduction. Here, this is formyl chloride. When formyl chloride is treated with hydrogen, palladium, and barium sulfate in presence of xylene solvent at the temperature 144 degrees Celsius, then formyl chloride is supposed to convert to formaldehyde through Rosenmund reduction. But this formaldehyde is not produced from formyl chloride because formyl chloride is unstable at room temperature. It breaks in HCl and carbon monoxide. As this is unstable compound, through Rosenmund reduction from formyl chloride, formaldehyde cannot be prepared. This is limitation number 1. Number 2 is Rosenmund reduction is used to prepare aldehyde, not ketones. So limitations are formaldehyde cannot be prepared from formyl chloride through Rosenmund reduction, and through Rosenmund reduction ketones cannot be prepared. This is all about Rosenmund reduction. No more today. Thank you very much.